So hello everyone, welcome to the second talk of this 7 to 9 session. So the speaker for this session is Professor R.Srikant, sorry. So a bit of a background of Professor Srikant. So Professor Srikant is the co-director of C3.ai Digital Transformation Institute and the Frederick G. and Elizabeth S. Nearing endowed professor of electrical and computer engineering and coordinated science lab at the University of Illinois at Urbana-Champaign. His research interests include machine learning and communication networks. He is a winner of the ACM Sigmetrics Achievement Award, the IEEE Koji Kobayashi Computers and Communication Award, and the IEEE Infocom Achievement Award. He has won several Best Paper Awards, including the Applied Probability Society's Best Publication Award, the IEEE Infocom Best Paper Award, and the WIOP Best Paper Award. So today, Professor R.Srikant would be speaking on the role of lookahead and approximate policy evaluation in policy iteration with linear value approximation. Sorry, linear value function approximation. So Professor Srikant, please go ahead. Thank you.
Thank you, Gugan, for the nice, kind introduction. So this is joint work with my graduate student, Anna Winnicki, and a former student, Joseph Lubars, who recently joined Sandia National Labs, and Michael Livesay, who's also at the Sandia National Labs. So Anna did much of the heavy lifting for this work. So this is a workshop on reinforcement learning. So I'm sure everybody knows what reinforcement learning is. But just in case somebody's here to learn, I just want to have one slide sort of giving a very high level picture. So in reinforcement learning problems, you have an agent. The agent takes an action. The action changes the environment that the agent is in, which is called the state of the system. And in response to the action, you observe the new state, and you also observe the reward that you get by taking that action in that particular state. And the agent then takes a new action and so on. So you have to learn through usually training ahead of time what the right actions to take in. So I am going to focus in this talk on the difficulties of very large state spaces. In particular, in reinforcement learning, one can find the optimal policy by using what is called a tabular method. So in a tabular method, for each state, you store some information and use that information to figure out what the optimal action is in that state. Of course, as Sean mentioned chess in his talk, this is infeasible when the state space is very, very large. For example, there's something called the Shannon number for chess, which is 10 power 120, which is the number that Shannon computed is the approximate number of possible states in chess. So tabular methods are infeasible. And so the focus of this talk is what can one do about the fact that the state space is very, very large. So we want to avoid high memory and time complexity for very, very large states. So as an outline, I just want to mention a few brief things that I'm going to touch upon today. So in practice, people use a number of tricks to tackle the very large sizes of state spaces in oral problems. Okay, and they go by many names. Some of them are similar, some of them are very different from each other. Something called look ahead, rollout, m-step return, doing a one step of gradient descent occasionally, and so on. So I want to understand in a quantifiable manner how these tricks are useful when you have to deal with problems with a large state spaces. Okay, and I will restrict my attention to linear function approximation. And I'll explain what that means. And hopefully that'll shed light on neural network-based approximations. And I will briefly talk about that as to why I believe that that is the case. Okay. And I will focus in this talk on approximate dynamic programming. I'm very glad that I'm following Sean's talk, because in my talk, I am going to assume that the model is known, the MDP is known, and you just simply cannot solve it using standard techniques like policy iteration, value iteration, and linear programming, or anything like that, simply because the state space is very, very large. So many of the RL success stories fall into this category. Certainly in the context of games, for example, in chess, everything is known. I mean, there is nothing uncertain. I mean, of course, it's a game situation, so the opponent will play a different move. But every time anybody takes an action, you know exactly what the next state is going to be. So I'm going to assume that the MDP model is known, meaning the probability transition matrices are known. And the main difficulty I'm going to focus on is what happens with very large state spaces. This very much complements Sean's talk, where he talked about, you know, what if you don't know the model and you have to use stochastic approximation to tackle the issue. And it's an interesting question as to how one can use the ideas in this talk in a complementary fashion with stochastic approximation to study problems where both the state space is large and you have to learn either the model or not really the model, but something about the value function without knowing the model. So I just want to mention a few related works. I mean, many of the foundations for what I'm going to talk about is in the many wonderful books of Dmitry Bertsikas. In particular, he has a recent book on RL and optimal control, which nicely blends theory and practice. And I think it's a great read. And I think I'll mention the main result that we have. There is a certain similarity to one of the results in Bertsikas' book, and I'll mention that later on. The paper that's the closest to what I'm going to talk about is a recent paper by Efroni, Delage, and Shai Manor. And so they considered these tricks called Lookahead, this trick called Lookahead in policy improvement and policy evaluation, but they don't consider function approximation. So their result essentially says how policy improvement and policy evaluation, Lookahead can improve performance. But what I want to point out is that the results change dramatically when function approximation is used. And in this case, Lookahead is not just used to improve convergence speeds or accuracy of your results, but actually it is needed. Without that, the algorithm may not even converge. And that's one of the points that I'm going to make. And the lack of convergence with function approximation goes back to a very simple example that Tsitsiklis and Van Roy concocted in 1997. I don't know if there are other examples, and there may be other examples before as well. But so our motivation for the counter example was this paper by Tsitsiklis and Van Roy, where they're not trying to find an optimal policy, just simply trying to evaluate a policy using policy iteration, evaluate the value function associated with policy. Okay, so underlying everything I'm going to talk about is a Markov decision process. I'm assuming most of you know what they are, but I'm going to assume finite action and state spaces. However, the main difficulty is that the state space is very, very large. And I'm use pi to denote a policy, and I'm going to use the standard discounted total reward, where alpha is the discount factor. And I'm assuming that the transition matrix P is known to us. So the goal is to maximize the total expected reward, or find a policy pi that maximizes the total expected reward. By the way, I realize it's very late in the evening in India, so I'll try my best to keep my talk to about 40 minutes or so, so that you have some time in the evening. So the goal, of course, I just want to introduce some notation. Again, these are all standard things. So J star of S is the optimal value function starting in state S. So let me actually pull up my pen. Yes, I want to. Okay. And TJ is the standard Bellman operator. It's you can also think of it as a policy improvement operator. So if you're given a particular value function, if you want to find a policy that sort of improves on this value function, what you could try to do is just assume this is the correct value function and try to find a new policy that maximizes this expression. So this is the Bellman operator that takes J and produces a new J, and in the process also gives you a policy. And this we will call the greedy policy. And just one more notation. I mean, instead of the optimal Bellman operator, there can also be a Bellman operator associated with a particular policy. Let's say in this case, I don't know why I switched to using mu here. So if mu is the policy here, then J mu is the value function associated with that policy, and this is the operator whose fixed point gives you J mu. And similarly, the fixed point of the Bellman operator on the previous page will give you J star. I'll try to keep the talk somewhat pictorial. So I just wanted to introduce some notation, but after that, hopefully most of it will be pictorial. So let's just briefly recall what policy iteration is. And I think all of you know what policy iteration is, but I want to show it in the form of a picture so that the rest of my talk I'll illustrate using similar pictures. So in policy iteration, you have a policy, some particular policy mu. You have a value function associated with the policy. And then you get a new policy, mu k, from this value function. And you evaluate the new policy to get a new value function. Okay, so there's a policy improvement step here, followed by a policy evaluation step. So how is it done pictorially? So basically, so if you're so let's say you're interested in evaluating the policy at this state x0, and let's just, so throughout I'm just going to, for simplicity, I'm going to consider the case of deterministic transitions. There's no MDP, it's just a large dynamic program. Many of the ideas can be illustrated through pictures here. And so the idea is that you are interested in finding the optimal policy for state x0, and there are 4 possible actions indicated by these arrows. So what you might do is that if I go along this arrow, then the immediate reward is R, plus the future reward is alpha times this. So I add the 2, and then keep track of that. And then for the next action, I do the same. I do this for all 4 actions. Then I find the largest one, the one that gives you the largest value. That would be my new policy. So this is the policy improvement step. In the policy evaluation step, what you do is for each state, one could potentially do this, which is, so you start with the state x0 again. If you're in the state x0, you follow your policy, find the path that it takes through this dynamic programming tree, and then you keep adding up all the costs, multiplying by the appropriate discount factor to estimate the value function at node x0. Okay, so this is very simple, right? And if the number of states is, let's say, 10 or something, and if it's an MDP, you can potentially do this. But obviously, you cannot do this when the number of states is 10 power 120, like in chess, right? So you have to do something else, because you cannot evaluate the policy possibly for every. So you have to evaluate the policy for this state. I just showed you. Along the path, you already can figure out the value function, but then you have to do it for all these other states in the system. In the MDP, which is infeasible. So what do you do? So just to summarize what we just talked about. So one difficulty with implementing policy iteration in very large spaces, large state spaces, is that you need to compute, evaluate the policy at every state, and this is clearly infeasible when S is very, very large. So therefore, the purpose of this slide is to illustrate that if you're playing tic-tac-toe, of course you can do this because the number of states is large, but if you go from left to right, if you're trying to play chess, then of course the state space is so large that you cannot do this. So you have to do function approximation, and here LFA stands for a linear function approximation. Okay, so one possibility, I mean, so instead of, so there are 2 parts to policy evaluation, where you start from a particular node, follow your policy, go all the way to the end, and figure out how much reward you accumulated. Instead, what you could do is you could just add up the rewards for m steps, and then simply use the previous estimate of your value function at that point. So this is called an m-step return or m-step look ahead. So different people use different terms for this, or rollout. The terminology seems to be somewhat non-standard, especially between practitioners and theoretical papers. But basically, you can look ahead m steps, evaluate your policy. So instead of going all the way to the end, that's one thing that could save some computational complexity. So here's an example. You start here, and then you m equal to 3. You just go down this path, and then stop here, and then add up the cost at this point, and then use that as your estimate of your value function. Okay, so but what about other nodes? So you have to do this for every node. So even if you're not looking all the way down the tree, you still have to do this for every node, and so therefore this is infeasible. And so a possible solution to this is, so a possible solution to this is to assume that there is some parameterization of the value function. So you assume that the value function is of the form, value function at a node I is of the form theta transpose some feature vector phi of I. And the goal is to estimate the right theta for your value function. So here I'm going to assume that these feature vectors are given to you. In practice, neural networks are used. But if you believe, some of you may know this, there's something called the neural tangent kernel approximation, which is essentially a way to linearize neural networks. I think for people who are control theorists, this is a standard way to study nonlinear systems. You linearize it, and then you study its stability, and then you show that if the original nonlinear system is a small perturbation from the linear system, it'll still be stable. And this is precisely what the NTK approximation does. It basically linearizes the neural network around the initialization, and then you argue that that actually is very close to a linear function approximation. So I believe everything that I'm talking about today also applies to neural networks, and which is consistent with the title of this workshop. But we have not done that, and this is the next step that we are thinking about currently. Okay, so but given a set of feature vectors, okay, so instead of evaluating the value function at all nodes, let's say we evaluate the value function only at a subset of the nodes each time, okay, then you can solve a least squares problem to find the best theta, okay. And so you have an estimate of the theta, and so now using this estimate you could figure out the value function of all the nodes, and you can repeat this, right? So you can keep doing policy iteration in this manner. So instead of evaluating the policy at all nodes, evaluate it at a few nodes, find the best linear function approximation based on those estimates, and then do the policy improvement step, and then go back to policy evaluation, approximate policy evaluation again. So the question then is, does this converge? And the answer is no. And this is where we used a very simple example motivated by Tsitsiklis and Ben Roy, although their motivation was not to find an optimal policy, but a small extension of their algorithm suggests that, I'm not going to go through this example. It's a very simple example, two-state Markov model. There are only two policies, and you can easily show that there is divergence here if you use the scheme that I just said. If you do one step of policy evaluation, if you do one step of policy improvement followed by policy evaluation using function approximation, and then you keep doing this, this will not converge. In particular, the algorithm diverges whenever delta 1 times alpha power m is greater than 1. So delta 1 is just something that depends on the feature vectors. It's in some sense a measure of the quality of your feature vectors, and alpha is the discount factor, and m is the amount of look ahead you use in policy evaluation. So if m is very large, okay, or if m is large, it doesn't have to be very large. If m is large, clearly this condition will be violated, and then there's potential for convergence. But if m is small, then this condition will be satisfied and the algorithm will diverge, because alpha power m keeps getting smaller and smaller as you increase m. So for m large enough, this condition will be violated. And this example certainly does not show that you have divergence. So the interesting question is, if this condition is satisfied, do you have convergence? Okay. Indeed, there is. So that's our main result. I'm calling it version 1 because I'll give you a better main result in a few minutes. So what we are able to show, not just for that example, by the way, there's nothing to do with that example. That example was just motivation. In general, if m is sufficiently large, where the amount by which how large should be is determined by the quality of the feature vectors that you've chosen, which is characterized by this quantity called delta 1, and the discount factor that you have. If m is sufficiently large, then what we can show is that if you do approximate policy iteration, where you use function approximation in the policy evaluation step, you can show that the value of the policies that you get compared to the optimal policy is less than or equal to Cm divided by 1 minus alpha. And the Cm decreases as m becomes large. But the issue with this is that Cm does not go to 0. Okay, so this result simply says that the larger the look ahead you have the function approximate or the policy evaluation step, you get better and better results, but it doesn't say that you will get close to the optimal policy. Okay, so the question is, so what does one do? And so this is the second trick that is used in practice. So the first trick is what I mentioned earlier. So basically, when you evaluate the policy, roll out the policy to m steps or look ahead m steps and use that as your estimate of the new value function, and use function approximation to complete the estimate for all the other states. Now, you don't actually do this for all the other states. Whenever you need to, you can call upon your function to approximate the value function for that state. But the second trick, to make the policy be better, you have to do look ahead in the policy evaluation step as well. Okay, so what you do is that instead of computing a greedy policy based on your current estimate of your value function, what you do is you look somewhat down your dynamic programming tree, and then it's not one step greedy, it's 8-step greedy. Okay, and what is interesting is that what we will the main result will show that if the combination of the look ahead for policy improvement, for policy evaluation, and the policy improvement, if the sum of these is sufficiently large, then you have convergence. So this gives you a trade-off. So you can choose large m's or large h's to ensure you have convergence, but or not. I guess I shouldn't say convergence. Actually, bounded error. Okay, so when I say convergence, what I mean is bounded error here. Importantly, increasing m actually improves the quality of your policy, but it doesn't actually help you find the optimal policy, whereas improving h actually pushes you towards, increasing h pushes you towards optimal policy. I'll get to all of that in a few minutes. Just as a matter of notation, as I mentioned, T is the operator, the Bellman operator, and when you apply T power h to j, it is called the 8-step look ahead. And the 8-step greedy policy uses an h-1 step look ahead, and then you find the policy based on that. Okay, so let me illustrate it using a picture. Actually, this is cleaner. So let's say what is a 2-step look ahead? So what you do is so you start with this at the top. Let's say you're interested in finding the new policy for x0. So previously, what we did was we looked at this action, the value function here, added these two up, looked at this action, the value function here, added these two up, whichever action gives you a better sum or weighted sum, then you take that to be the action of the state. In a 2-step look ahead policy, what you do is you go 2 steps down. So you take this action and look at the consequences of this action 2 steps down the road, okay, and see which of these paths gives you the best total value function, the best estimate of the value function, and then you take the action that gives you the best 2-step improvement. Okay, so if you keep doing that, so you do this at this node, again you look ahead 2 steps, at this node you look ahead 2 steps to find the next step, your best action, and then do this for each of the nodes. So this is 8-step look ahead, and of course 8-step look ahead is computationally very expensive. Of course, if you think of it as a tree, for example, and it's a binary tree, if you're looking ahead 8 steps, then your computational complexity will go up 2 power h. But in practice, people use something called Monte Carlo tree search, and this is well studied. There is a recent paper by Devavrat Shah, Xiaomin Xie, and Jiju, which shows that theoretically MCTS still has exponential complexity. You cannot get around that, but it works well in practice. So the works well in practice is not in that paper, but it's widely used. So I'm going to assume that we are going to be able to approximate T power H using MCTS, and this is also sort of the part of the motivation of the paper by Efroni and Shaimanor and so on. Okay, so what is our proposed algorithm then, which is sort of an abstraction of what is used in practice. So basically, you evaluate the policy for us at each iteration. You evaluate the policy for some subset of the nodes. Okay, and this subset can vary from one step to the other, to the next, and then you use a M-step look ahead in the policy evaluation and the H-step look ahead in the policy improvement to get a new policy that is evaluated only at a few nodes. Okay, and then you solve the least squares problem to get the new theta. Of course, in practice, you won't be using least squares, and I'll get to that in a second. Solving a least squares problem for a very large theta is actually, even though the dimension of theta is much smaller than the size of the state space, it could still be large. I mean, it could be in the millions in neural network models, for example, but it's still much smaller than 10 power 120. So you don't want to solve a least squares problem at every step, but let's just say for the moment that you solve the least squares problem. Then what is our main result? So what we show is that the combination of look ahead in policy evaluation and policy improvement, if that combination is sufficiently large, then when this condition is met, then you have an error and the algorithm converges of this form. Of course, it's all the rage in machine learning to give finite time bounds. So we have that in the paper as well. So you can, of course, you calculate finite time bounds to get the result as k goes to infinity. So if you're interested in what happens if you stop the algorithm after t iterations, we can also provide you an answer to that. So unlike before, where we only used look ahead in the policy evaluation step, if you use look ahead both in policy evaluation and policy improvement, this constant on the right-hand side, it not only decreases with m when may not go to 0, but making h large, you can make it smaller and smaller. So one has to judiciously do this, which is what is done in practice. So people roll out or look ahead for a certain number of steps in the policy evaluation and look ahead a certain number of steps in the policy improvement. And the amount of look ahead that you need is a function of the features. So this is where I believe neural networks play an important role, because I think neural networks find features for you that are very good. And so a combination of a well-chosen neural network architecture can potentially reduce this quantity, thus allowing you to control the computational complexity involved in doing these two things. At least that's my conjecture. And I just want to point out the relationship of this result to approximate policy iteration in Bert-Sikkes' book. The result is strikingly similar. So instead of the numerator in Bert-Sikkes' book, there are some parameters that quantify the approximation and the policy improvement and the policy evaluation step. And the denominator has actually 1 minus alpha square. So what our analysis says is that by using function approximation, I think the result in Bert-Sikkes' book is for abstract approximate policy. So we are saying that a particular approximate policy iteration using function approximation, or you can quantify what error is in this error, and you can understand the effect of m and h, this error. And instead of the denominator being 1 minus alpha square, you would like the denominator to be actually 1 minus alpha, because in the limit as alpha goes to 1, you would move 1 minus alpha to the left-hand side, because that's the only that makes sense, because you're looking at average cost in that case. And so you want the error to go to 0. The extra 1 minus alpha per h minus 1 essentially says that if you're using look ahead in the policy improvement step, you can actually get rid of the other 1 minus alpha that's here. Okay, or at least mitigate the effect of it, not quite completely get rid of it. You can mitigate the effect of the extra 1 minus alpha. So in the earlier analysis, like in Bert-Sikkes' book, what they point out is that if there is convergence of the policy, that 1 minus alpha term goes away. Here we are saying that we don't know if the policy converges or not, but just the very fact that you're looking ahead actually mitigates that term a little or significantly. Okay, so to comment on the result, to get better policies, you have to increase H. To get better policy evaluation, you increase M. And increasing M reduces the approximation error, but cannot make the error go to 0. Okay. However, increasing H can make the error become small. Of course, you can't do H very, very large because there's a computational complexity trade-off there. But you would use some reasonable H, which is a function of your feature vectors. And as I mentioned here, I want to emphasize the magnitude of the error depends on the feature vectors used in the function approximation, and the amount of look ahead that you have to do also depends on the on the feature vectors used in function approximation. And my conjecture is that neural networks produce better feature vectors than what we can do without any need for us to select the right feature vectors. And this is an interesting continuing topic of research. So that was sort of the main ideas behind the talk. And the rest of the talk, what I'll talk about is talk about how to further decrease the computational complexity using gradient descent, okay? And also give you some intuition behind the conditions that are in the theorem. So the proof is quite complicated. It uses every possible trick that you know in MDPs, but is somewhat involved. So I won't go through the proof, but I'll give you some intuition behind the conditions that are required for convergence in the proof. Okay. So as I mentioned earlier, solving the least squares problem can be difficult. So there are two choices. You can do a matrix inversion or run gradient descent. Sorry, it should be gradient descent to solve. It should be descent there to solve the least squares problem. But you might need a lot of, how many steps of gradient descent do you do? Okay. In practice, if you look at the at least the published codes of alpha 0 and so on, they do one step of gradient descent. So they evaluate the policy at a few nodes and then do one step of gradient descent to update your neural network parameters, in this case my linear function approximation parameters, and then move on. Okay, so the question is, does this converge? People call this stochastic gradient descent, but there's really nothing stochastic in it. All it is just one step of gradient descent. Okay, so previously I said we are going to use least squares to obtain the best weight vectors for our feature vector, for our feature vectors. So now what I'm saying is that what we are saying is that, so I guess I can't make my pen mark go away, sorry about that. So instead of solving this least squares problem, I'm going to just do one step of gradient descent. So I'm not solving the least squares problem at all. I'm trying to move towards the optimal solution by just doing one step of gradient descent. So does this have any hope of working? Okay, so the again, the idea is that you evaluate the policy at a few nodes, and then instead of finding the best weight vectors to approximate the policy that you have, the policy values, the values you found, what you do is just do one step of gradient descent. Okay, and then after you do one step of gradient descent, assume that the new theta that you have is the correct theta, and you keep moving on. So never do you solve actually the full linear the least squares problem. And somewhat surprisingly, what you can show is that the same type of result as before holds. Okay, the CMH that I have now might be slightly different. Okay, I'm just using the same notation, but it's slightly different. So you get a very similar result as before, that you get the error in your value function and the true value estimate is upper bounded in a very similar fashion, but an additional condition is needed. Not surprisingly, you need that the step size that you use for gradient descent to be sufficiently small. This is not surprising. I don't know what happens if you use decaying step size. Maybe you don't need this condition. I'm not sure about that. So currently we've just done for fixed step size at each step of gradient descent, and if the step size is sufficiently small, then you have quote unquote convergence or boundedness of the error, and the error can be made small by adjusting M and H. So I'm going to provide you some intuition behind the proof by considering a completely different problem. Let's talk about value iteration. It's sort of easy to understand why you would need a condition like this when you do value iteration. Quite hard to understand in the context of policy iteration. The proof is quite involved. It uses every possible property that you have of this Bellman operators. And the proof is even more complicated for gradient descent because you're not solving the least squares problem at each step, and you're doing one step of gradient descent. So you have to use properties of gradient descent in addition, in conjunction with the properties of a Bellman operator. But understanding approximate value iteration provides some intuition for the conditions required for convergence, and I'll just brief talk about that. So I think, again, most of you probably know what value iteration is. In value iteration, you take the Bellman operator and you just iterate it repeatedly. So you start with some initial estimate of the value function, pass it through the Bellman operator, get a new estimate, and you repeatedly do this. So as k goes to infinity, because the Bellman operator is the contraction mapping, you have convergence. Okay. An h-step version of value iteration is at each step you do an h-step. So you raise t power h. So you repeatedly apply the Bellman operator h times before finding your new value function. So this is the h-step look-ahead version of value iteration. So the question I want to ask is that what if I'm not doing this step of the iteration, but rather I'm only evaluating this step of the iteration only at a few states. Few just nodes mean states here. Suppose I evaluate it only at a few nodes and use function approximation to complete the rest of it. So basically what I'm going to do is I'm going to do value iteration for a few, value iteration using an h-step look ahead. And then I'm going to solve the least squares problem. Solving the least squares problem can be thought of abstractly. It's basically you're applying some operator to t power h jk to get your new jk plus 1. Okay, and this operator, of course, depends on your choice of the feature vectors. So the new algorithm that we have is jk plus 1 is m times t power h jk. So t is a contraction mapping with the contraction parameter alpha. So t power h is tjk minus j star decays at rate alpha. So if you apply t power h, it decay at rate alpha power h. And so therefore, if you go back to this iteration and look at it, we want to understand how jk plus 1 converges. It has a fixed point, and the convergence to the fixed point, just a very simple calculation shows that it is alpha per h multiplied by the infinity norm of this m operator, okay, induced norm of this m operator. And so therefore you have convergence only when this m infinity times alpha power h is less than 1, right? So this is equivalent to saying h should be sufficiently large. So the operator m depends on the basis function. So this is very similar to what happens in approximate policy iteration, but the proofs of approximate policy iteration are much more complicated. So I just wanted to give you some intuition as to what is happening here. So the conditions that we needed said that the look ahead has to be sufficiently large, and it should be a function, and it will be a function of the quality of the approximation that you that your function of, well, not the quality, but the quality of the quality of the feature vectors that you're using, and that's exactly what happens in approximate value iteration. And it's very easy to understand why you would need a condition like that. But what we show is that a much more involved calculation tells you that something similar happens in approximate policy iteration. Okay. So I'm going to conclude. As I said, I'll try to wrap it up in 40 minutes is what I said. I'm going to try to do that. So we have some numerical results here, which sort of illustrates illustrates some of the concepts that I mentioned here. And we used a simple n-by-n grid example that is in the Efroni, Dalal, Scherer, and Manor paper, just to point out the significant differences when you're using function approximation. As you can see, increasing h leads to boundedness of the error. Error keeps decreasing dramatically. I mean, the error just becomes unbounded. the error decreases if you increase either H or M, as the theory suggests. And of course, to show that the quality of the features matter, we considered random features and designed features. And you can see again that with design features, you get much better approximations than with random features. Ideally, of course, you don't want to design the feature vectors. In some problems, of course, you can, but in general, you would like a neural network to find it for you. We also, of course, you don't have divergence always. I mean, it depends on the initial condition. It depends on many features of the problem. But it is interesting to note that therefore we decided to plot from different initial conditions whether there's divergence. And as you can see, again, the quality of the feature vectors matters. For random feature vectors, you have very high fraction of the time you have divergence. For design feature vectors, you know, the results, the amount of look ahead that you need is not very large, and so you have convergence more easily. And of course, if you have tabular case, which is the Efroni, Delage, Scherer, and Manor paper, you always have convergence. So there's a striking difference between using function approximation and not function approximation, and you can actually quantify the effect of the various tricks that one can use to deal with the very large state spaces using our result. So there's one more result like this, and I'm going to skip this. So we analyze the impact of look ahead. In some of the literature, look ahead means look ahead to find the new policy or the policy improvement step, and they use the term M-step return for look ahead in the policy evaluation step. So we analyze the impact of look ahead and M-step return on approximate policy iteration with linear function approximation. We showed that large M plus H is necessary for convergence in the sense that you can have counter examples showing that if the condition is not satisfied, you don't have convergence. But if M plus H is sufficiently large, the error becomes bounded. And by choosing M and H large enough as a function of the representation power of your feature vectors. So somehow, if you choose good feature vectors, you don't need computational complexity, can be managed more easily. The paper is on arXiv, and if any of you have a chance to read it, we would love to receive comments. Ongoing work, extensions to neural network-based function approximation. We're thinking about how to do that if we have nonlinear features, especially as in neural networks, and we want to look at real nonlinearities such as the ReLU neuron, which is not even differentiable, and see what happens in that case. And we also want to incorporate stochastic noise. So instead of sort of a simple deterministic dynamic programming model or a model that, instead of knowing, here I assume that the probability transitions are known. And so what I'm doing here is approximate dynamic programming. But if the model itself is unknown, so then you have to do something more, and you have stochastic noise, and so you have to use stochastic approximation techniques like in Sean's talk. And that would be an interesting extension to consider how to do a combination of approximate dynamic programming with true reinforcement learning in some sense, where you're actually trying to solve a problem where the model is unknown. Thank you very much, and I'm happy to take questions for any.
For the wonderful talk. I think Professor Mine has a question. Professor, go ahead and ask a question.
So Srikant, congratulations. I mean, for
Thank you.
Wonderful results and just a beautiful tutorial as well. I just loved it. But one comment for everyone is that I think that the community has let us down with these 1/1 minus alpha bounds. Because, so that was the point of this recent paper with Aditya, that it's just a constant that's making it blow up. So if you look at your,
but it's not blowing up though, because actually if you let alpha go to 1, the right thing to compare is the average cost, right?
No, well, that's what well, the point though is that if you take your estimate minus its value at one point, and then take the true value function minus its value at one point, the difference of that's what's meant by relative, relative TD learning. That difference will be bounded in alpha as alpha goes to 1, because each of the terms is bounded in alpha, and so. But
I guess what I'm confused about is this. So if there's a 1 minus alpha square on the right hand side, there is a problem. But if it is just 1 minus alpha on the right hand side, it is not an issue because you have to multiply by 1 minus alpha to get the average cost anyway. So our result would say that.
I'm just saying that maybe it's not true. So I conjecture that there's only one. See, what if it was in many dimensions? See, when you present a constant of 1 minus alpha, it suggests there's a problem. But there is a problem. I'm saying it's a problem. If you can't subtract it away with a single constant, then you've got a problem. And you see what I mean? And so
I have to think about this. I guess I'm a little confused because I thought about this. Okay, I know you've talked about this before in the Simon's workshop too, and I understood it at that time, but I have to think about it a little.
So if I was wrong, if it wasn't that in both, if you just normalize by constant for both functions, then they're both bounded and the problem solved. You know, if it was more complicated than that, then there'd be a reason to really fixate on that 1 over 1 minus alpha.
Okay.
You know what I mean?
So here, this is approximate dynamic programming, so I'm not doing any kind of estimate of anything like PD.
Right. Yeah.
So I think
I bet the relative guys is no 1 over 1 minus alpha there. That's you know, or 1 over 1 minus alpha squared. They're all gone, and you don't care about constants anyway. So anyway, it's just a comment for the community.
Okay. Thank you.
Yeah.
Okay, thanks. So Dimitri had a question.
Yeah, let me just figure out the controls here. Yeah, very nice talk, Srikant. And what I'd like to say is that the idea of having a combined look ahead, M and H, look ahead with minimization and look ahead with a base policy, that's a very important idea. And it also underlies the first major success story of reinforcement learning, which is 25 years ago. In backgammon, the program by Tesoro. Tesoro introduces this idea of doing look ahead by minimization and also look ahead with some policy. And that's how Tesoro's programs rose from having subhuman performance level to superhuman performance level. It was a very important idea. And I think the context, and coincidentally, the next talk, which is mine, is going to have to do with this idea, although it will approach it from a different point of view. Now, I've noticed that that you're using this combined look ahead in a policy iteration context, which is relevant and important there as well. But it's also very effective in just online play, online generation of controls. And still there, it improves performance very much.
So you're saying in real time when you're
I'll
playing?
leave it here.
So are you saying in real time? I mean, so you don't have to even train, but you could just play online, is what you're saying? I see.
Yeah, play online, but the policy that you have and the cost function approximation that you have at the end could be obtained by offline training, which is what Tesoro has done. Tesoro used the policy iteration and neural network approximations to obtain a default policy and a cost function evaluation, an evaluation function in the context of Gamma position evaluator. So he bootstraps the results of the offline training to play online, but still with combined look ahead. And that's what made all the difference in Tesoro's program. And there are similar ideas also that apply to AlphaZero. I think it's an idea that applies very broadly, and I think it's worthy of attention by the community.
I guess, yeah, I missed the point. I think what you're saying is that I've only focused on the training part of it. You could also, once you find the policy, you should also still use a look ahead when you're actually implementing it, and that can further improve performance at this point. Thank you.
Exactly. Yeah. The main improvement actually is obtained through online play.
Right.
But it's important to use also offline training to sort of improve the starting point for the online play algorithm.
Okay, great. So my talk is focused on the offline part, and I think the additional thing that we do is look at quantifying what happens. Great.
That's right. Yeah.
Chandra has a question.
Yeah. Hello. Hi, Srikant. Yeah, it was a nice talk. Am I audible?
Thanks. Yeah, thank you. Yeah,
Yeah.
I can hear you.
Okay. So what I understood that you suggested evaluating policy at a subset of nodes at each step.
Right.
Let's say any rule for selecting that subset, or how does the size of that subset would impact the error bounds?
Very good question. Actually, the parameter delta 1 quantifies all of that. I don't have a good selection rule. It just simply the parameter functional approximation capabilities of the feature vectors and the quality of the states you're evaluating. So in practice, what one would do, at least in alpha 0 kind of thing, the way I understand it, is that you just play Go or chess to completion, and then you just see whatever states you see. So you don't have much control over which states you're evaluating, and that works pretty well. It'd be nice to be able to quantify that better. You just
so it's again a classical offline versus online problem in RL. So you suggest that one could go for an online version where whichever states you encounter, you evaluate the policies there.
Correct.
Right. But still, how many nodes to pick at each step? Well, will it be one?
In chess, you always start at the same starting node. You go to the end, and then you do it again, and then you just hope to visit a rich enough set of states. Our results basically say that your quality of the function approximation will depend on what kind of states you pick, but I don't have a prescriptive way to figure it out. In some games, I think people can start at a random initial state, and then they would just have some kind of exploration in that manner. So you just start at a random state, go to the end, start at some another random state, and go to the end. But I believe in AlphaGo and AlphaGo 0 and Alpha 0, I think they just simply start from the beginning and go to the end. Yeah.
Okay, thank you.
I don't know if there are any other questions.
So we don't see any raised hands. So thank you, Professor Srikant, once again for the wonderful talk. Thanks a lot. I'm sure everyone really enjoyed your talk. Thank you.
Thank you, everybody.